Alright, today we're going to be talking about thermodynamics, and often in thermodynamics you see the equation delta G equals delta H minus T times delta S, which is commonly known as the Gibbs free energy equation. In which cases will delta G be negative or spontaneous due to the value of entropy?
So here we have an entropy problem. We have 2 moles of sulfur dioxide, which is the gas, and 1 mole of oxygen gas. And on the product side we have 2 moles of sulfur trioxide, which is the gas. And because you have 3 moles of a gas on the reactant side and 2 moles of a gas on the product side, there'd be a decrease in entropy. For this third equation, we have on the reactant side 1 mole of carbon monoxide, which is the gas, and 2 moles of hydrogen gas. And on the product side, we have 1 mole of methanol, which is a liquid. And because a gas has a higher entropy than a liquid, we have 3 moles of a gas on the reactant side and 1 mole of a liquid on the product side, so there'd be a decrease in entropy.
When increasing the temperature, volume, or the amount of a substance, that often results in an increase in entropy. But if we refer back to our Gibbs free energy equation, you can see that if you increase the temperature, obviously you're going to have a higher chance of having a negative delta G.
For the second equation on the reaction side, we have 1 mole of barium hydroxide, which is a solid. And on the product side, we have 1 mole of barium oxide, another solid, and H2O gas. And because we have a gas on the product side, which has a higher entropy than a solid, this would be an increase in entropy.
Alright, so what is entropy? As I said before, entropy is the disorder within a system, but it's more than that. So think of entropy as 2 different scenarios. One based in a school, the other based in this classroom, for example. And think of yourself as a molecule. And in the room, your movement is kind of limited, but in a school, you have many different places to be. You have hundreds of rooms in the school, and the school can represent a high entropy, because when the entropy is higher, that means that there's more disorder, except don't really think about it like that, but there's just more places for that molecule to go, more movement, and in that single room, there's low entropy and low movement.
Alright, when doing an entropy problem, you need to remember products minus reactants. That's the key concept. So for the first problem, we have 1 mole of hydrogen gas, which has an entropy of 130.5, and we have 1 mole of fluorine gas, which has an entropy of 202.7. Now on the product side, we have 2 moles of hydrofluoric solid, and because we have 2 moles, we multiply its original entropy, which is 173.51, by 2, and we get this equation problem product. For the second problem, we have carbon graphite, which has an entropy of 5.69, and we have 2 moles of chlorine gas, and the original entropy is 222.96, but again, because we have 2 moles of it, we have to multiply the entire entropy by 2. And for the products, we have carbon tetrachloride, and it has an entropy of 309.4. So the equation would be this: 309.4, which is the product, minus 451.61, which is a sum of the reactants, and that gives you negative 142.2 joules per mole Kelvin.
Alright, time for some review now. What is entropy? Entropy is a disorder within a system, but it's also the places where a molecule can be at one time. For delta G and entropy, the higher the temperature, the more likely delta G would be negative because of the entropy. And for entropy in the calculations, it's just simply products minus reactants. And remember, if you still don't understand this, refer back to chapter 19 in your blue book.